Hello and welcome to the first of the lectures in this week 12 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will look into some of the functional equations or inequalities involving fuzzy logic connectives. The motivation for this stems from the fact that we have always considered residuated lattice to supply us with the operations that we were employing in the inference systems. So quickly, what is a residuated lattice? As an ordered structure, it's a bounded lattice. As an algebraic structure, it's an ordered commutative monoid with identity 1, and the star and the arrow operations, they form an adjoint pair. That means they satisfy this particular residuation principle. And when we are considering fuzzy logic connectives which can lead up to a residuated lattice structure on the 0-1 interval, we saw that left continuous t-norms were the ones that were giving rise to the residuated lattice structure on the 0-1 interval. Now let's look at the role of such functional equations or inequalities. In the last few weeks, we have discussed many desirable properties of a fuzzy inference system. We began by looking at interpolativity of FRIs. So there again, we started with a single CISO rule, single input, single output rule, and we found that these were the two functional inequalities that were coming into play. What's a functional equation or an inequality? Here, let's look at such an equation where f we know is from R to R. Now here, in this equation, what we want to find is such a function f which will satisfy this equation. So in the given equation, the solutions of the equation, we are searching for it in the space of functions. So what we are interested in is finding such f which will satisfy this equation. It can be easily shown, this is known as a Cauchy additive functional equation, that with some reasonable assumptions about continuity on f, it can be shown that the only solutions are such functions. F of x is equal to kx, where k is a constant. So functional equations essentially are equations involving functions where we are looking for functions which will satisfy the equation. So in that sense, if you're looking at it, these are two functional inequalities because instead of equality we have an inequality, and what we are doing is over the entire range of alpha beta, which in our case is the unit interval 0-1, we are looking for t and f, functions t and f that will satisfy this inequality. And what we found was, when we consider the residuated lattice structure, these were two properties that were already available for us when we consider t to be star and f to be the corresponding residuated implication. When we discussed multiple CISO rules, we moved into looking at the inference process itself, the composition itself, and looked at it as dealing with fuzzy relational equations. And to discuss the solvability of it, we found that these were some of the inequalities that or properties from residuated lattice structure that helped us in discussing the solvability issue. When we move to continuity, when we first discussed continuity of CRA, you may have noticed these are the properties that we employed in the proofs of the different results that we actually discussed, and these were properties that were coming from the residuated lattice structure. In the case of continuity of BKS, when we discussed those results, we found that there was another set of properties from the residuated lattice that we were actually using. You may have seen that there is one particular equation that is highlighted in blue. It is only to show that it keeps recurring again and again. When we discussed the robustness of an FRI, again this equation came up. Of course, there were also many other properties that we made use of. There's another property, interesting property, which is highlighted here in red, which also kept recurring. It is not to say there's other properties which are not colored are not useful. In the context that we have discussed, these are perhaps two important properties that have come up again and again and helped us in our research. Now, These are some of the properties that we have used when we discussed robustness of CRI and BKS. Then we took a different perspective and looking at FRI as a fuzzy mapping between f of x and f of y, we asked the question, what is interpolativity? And there we found that we could just discuss about interpolativity not from the point of view of solvability of FRIs, fuzzy relational equations, but from the point of view of a mapping of AI to BI. And in that sense, all we needed was to look at R and the composition. And once you fix the composition, the question was, why not consider any R that is admissible based on whether it is interpolative or not. So we were trying to break the shackles of ourselves from R check and R cap. And you may recall that at that point of time, the by implication played an important role because we defined what is called a delta function there based on the by implication, and we showed that by implication is an equality or equivalence relation, and this is the property that played a role there. When we came to monotonicity of FRIs, we saw that the left neutrality property and ordering property played a role, which obviously we knew that residuative lattice structure was able to supply us with implications having these two properties. And when we discussed theta and phi, their equivalence, once again we saw that it is this what we call the distributive equation that came into picture. Now, you may have seen that under this different perspective, what we wanted to do was, we were trying to do some kind of a generalization. We came out of residuative lattice structure in the case of monotonicity and say, why not consider implications that have OP and NP? And in the case of interpolativity, we wanted to come out of solvability of FREs, and then we asked the question, okay, why not consider some R which is interpolative as admissible R? Now, taking cue from this, we would like to ask two questions. We have seen among all the properties, obviously we are using properties or equations or inequalities typically involving the T-norm and the implication, because that's what we have always been using. Now, it begs two questions. The first question is, can we extract the essential properties in terms of functional inequalities or equations to ensure desirable properties of an FRI, even when these operations that we consider, F, G, the aggregation operator, T or I, they are not chosen from a residuative lattice structure? So this is one question that we can ask. Essentially, we are discussing generalizability of the results that we have got. The second question that we can ask is, do some functional inequalities and equations, do they also have an impact on the computational complexity of a fuzzy inference system, of an FIS? So this is something that we have not seen so far. In this week of lectures, we will see this. So far, we were interested in finding out whether they had some desirable properties like interpolativity, monotonicity. There, you could think of them as really not related to the computational aspects of it, more on the correctness aspects of it. So we would also like to look at whether some of these properties, if they are enjoyed by the operations employed in the FIS, whether they lead to some computational efficiency. So these are the two questions that we would like to address during this week of lectures. So what are the functional equations we are going to consider? So the first is the distributivity equation. We have seen this. So now, writing it in terms of fuzzy logic connectives, it would look like this. We could consider the distributivity either at the antecedent side or the consequent side. So this is called the antecedent distributivity equation. So now you see here, instead of max, we are taking a T conorm S. Instead of min, we are taking a T norm T. Now the question is, you will see that on the left hand side you have one operation, on the right hand side you have another operation. So is it warranted? Well, let's consider an equation of this type. So instead of S, let's put F1, and instead of T, let's put F2, and then try to fix what these operations could be. So what we have here, I of F1 of xy, z is equal to F2 of xz from I of yz. Now we need to fix F1 and F2 be either T norms or T conorms. So let's assume that F1 is a T column. That means what we know is 0 is in fact a left neutral element, a right neutral element, because S is commutative. So let's take x to be 0 in this equation. So then that equation reduces to f of 0 comma y comma z. This becomes f2 of I of 0 comma z comma I comma z. Now we know that I of 0 comma z is 1 because I is an implication. So that means this is f2 of 1 comma I of yz. On the left hand side, what we have is, because this is y, what we have is I of y comma z. So what we see from here is f2 of 1 comma Iyz is in fact equal to I of yz. And this should happen for any yz, arbitrary yz, which means 1 becomes the neutral element of f2, which in our case, since we are considering only operations coming from T norms and T conorms, it is clear that f2 is a T norm. So that is why we have taken, when we take S here, it automatically translates it as fixing the right hand side operation f2 as T. Similarly, easily it can be worked out that if you take T here, then it will become a T conorm on the right hand side. Well, this is antecedent distributivity. On the consequent distributivity, similarly it can be shown that the same operation can be retained, because it is also clear because I in the first variable is non-increasing, so essentially it is going to flip it, it's a decreasing function, whereas in the second argument it is increasing, so that means it retains the same order, so T remains a T and S remains an S. So this is one equation that we would like to discuss now. So let's look at, given T and S and I, we need to discuss what kind of, we want to fix T and S given I is an implication. So now, how do you fix on this T and S? Can we arbitrarily use any T and any S? So now, we need to make use of the properties of the implication. We have only fixed I, and based on that, we want to know what T and S could be. So to begin with, let's assume that I satisfies neutrality property. That means I of 1 comma y is y. Now, let's take this equation. I of txy comma z is equal to s of ixz and I of yz. Now, if you take x is equal to y is equal to 1, then what we have here is I of t11 comma z is equal to s of I1 comma z comma I of 1 comma z. Now, we know that T is a T norm, T of 1, 1 is 1. So this is I of 1 comma z. But I of 1 comma z, on this side, I of 1 comma z is z. And this is z. And this happens for every z element of 0, 1. So this implies S of zz is equal to z, implies S is idempotent, which means S is in fact the max T norm only, because we know that the only idempotent T conorm is the max T conorm. So if we fix I to satisfy an extra property, that of neutrality property, we immediately see that S becomes the maximum T conorm. Well, so now this equation, instead of S, we substitute max, and of course I should have neutrality property. Now let's take Ni to be strong. Other than I having the neutrality property, we insist the natural negation of I. Recall Ni of x is essentially I of x comma 0. This is strong, that means it's involutive. Ni of x. So now consider this equation now. This is max of I of x comma z comma I of y comma z. Let's take z to be 0. Then the left hand side becomes Ni of txy is equal to max of Ni of x comma Ni of y. Clearly this means T of xy is equal to, since Ni is strong, we could apply Ni on either side. So this Mi of max of Ni of x comma Ni of y implies T is the Ni dual of max, implies T is in fact equal to min. So just by imposing these two conditions on I, that I has neutrality property and Ni is strong, we are able to reduce T and S to that of min and max. So we have found solutions to this equation in terms of what T and S we can use so that this equality is valid. Of course, we have put some conditions on I. Now, the question is, what are those families which offer such implications? Implications with I having implications which have the neutrality property and their natural negations are strong. Clearly, Sn implications with strong n, because we know that Sn implications are given like this. If we know that the corresponding Ni, natural negation nothing but the n that we consider, and we know that Sn implications do have neutrality property. So if we consider Sn implications with strong n, these are also called S implications in the literature. So any S implication will fit the bill. Of course, we know that R implications with strong natural negation will fit the bill. Also QL implications with strong negations, they will also satisfy this equality. Now what is interesting is, in fact, if we fix T to be min and S to be max, it can be shown that any implication will satisfy this distributivity equation. This is nothing extraordinary. As was mentioned, it is decreasing in the first variable, so it just flips over there, and min and max are operations available on the lattice operations available on 0. So this can be easily proven. So now what it shows is, if you're looking at using the distributivity property, then perhaps you don't have to stick yourself only with operations coming from distributive lattices or R implication, but now you have a plethora of implications coming from different families which also satisfy this distributivity equation, and in some context where the distributive equation plays a role, you could freely choose from implications coming from these families too. Similarly, if you consider the consequent distributive equation, now once again we argue like this. Let's assume that Ni is onto, this is the equation that we are considering. We need to fix S now. So now we have Ni is onto. Now let's take Z to be 0. Then what we have is I of x comma y is equal to we'll take x, y is equal to z is equal to 0. Then what we have is I of x comma 0 is equal to s of x comma 0. Now this is Ni of x is equal to s of Ni of x comma Ni of x. Since Ni is onto, this implies for every y in 0 1, there exists an x in 0 1 such that y is equal to Ni of x. So now this implies y is equal to s of y comma y for every y in 0 1. This implies s is idempotent, implies s is equal to max. So by just assuming that the implication that we are considering is such that its natural negation is an onto negation, we can show that this S essentially boils down to being only max T comma. In fact, it can be shown once again that any implication satisfies this equality when S is max. So this is about the distributivity equation. Now what is the other equation that we had colored in blue? It is called the law of importation. We have referred to it like this many times in the earlier lectures too. Let's look at some families of fuzzy implications and then discuss whether these families do satisfy the law of importation. So let's start with the familiar ones. We know that SN implications are obtained from the material implication, essentially negation P or Q. That's what we generalized into S of Nx comma Y. S is a T conorm and N is a negation. We have seen R implications. One way to look at them as is from the set theoretic equality of A complement union B, and that's how we generated the corresponding formula for an R implication. F implications were obtained from additive generators of T norms. So we have a function f 0 1 to 0 infinity, which is strictly decreasing, continuous, says that f of 1 is 0. And we have seen that if you define a function if like this, f inverse of x dot f of y, with understanding that 0 dot infinity is 0, then we have seen that this is a fuzzy implication, which we called an f implication. Now we have also seen at that time that f of 0 may be infinity or it may be finite. Either way, if you take when there is finite, f of 0 is finite, then instead of considering the f, you could also consider f1, which is the normed generator. So essentially it normalizes the range codomain to 0 1, because now it's f of 0 is finite. And we have also seen that whether you generate the f implication from f1 or I or f, both are essentially the same. Similarly, we have seen G implications, which are obtained from the continuous additive generators of T conorms. So here G is a strictly increasing continuous function with G of 0 is 0, and the corresponding implication, the G implication, is given by this formula, and we're taking this convention. Now let's look at the law of importation for these four families. That means if you take I to be coming from one of these families, what should be the T? Does it actually have a T such that this law of importation is valid? And if yes, what should be the T norm T? Now, in the case of R implication, we have seen that T is T star. So there is it does satisfy law of importation, and T is equal to T star is the only solution that we would get. Of course, here we are talking about R implications from the residual lattice structure, means the T is left continuous. Now let's look at SN implication. Here it can be shown that so note that this S implication, that means the N that we are considering is strong. We can be shown that the T that we consider should be the N dual of S. It can be easily seen. So what we are looking at is I of Txy comma z is equal to I of x comma I of yz. Now this I is ISN, which is given as S of Nx comma y. So if you substitute here, then LHS is S of N of Txy comma z is equal to S of Nx comma, by the associativity of this thing, we can remove it later on. So now let's take z to be 0, and clearly this means N of Txy is equal to S of Nx comma Ny. Clearly that means since N is strong, T of xy is N of S of Nx comma Ny, which means T is the N dual of S. So not only S implications satisfy the law of importation, if they do satisfy, then the T has to be the N dual of the corresponding S. So the moment you fix S and N to be strong, then you know that with respect to its N dual T, it will satisfy the law of importation. Now what about F implications? Note that F implications are given like this: IF of xy is equal to F inverse of x dot f of y. So now the formula that we are looking at is IF of Txy comma z, is it equal to IF of x comma IF of yz. Now let's assume that it is true then we need to go and find out what is the t for which this is true. So now expanding this, what we see is f inverse of t of xy dot f of z is equal to f inverse of x into f of f circle f inverse of y dot f of z. Now, f we know is continuous and strictly decreasing, so we could perhaps cancel it out. This f circle f inverse, they will get cancelled. So what we are left with is t of x comma y dot f of z is equal to x dot y into f of z. Clearly, if you take a z such that f of z is not equal to 0, for instance, we know that if in the case of, clearly there will exist a z such that f of z is 1. So if you assume that, or any non-zero value here, you can cancel this, and what we say is t of xy is in fact equal to x dot y for any arbitrary xy that we have considered, which means t is in fact the product t naught. Similarly, it can also be shown for the G implication. It does satisfy the law of importation, and the t that we are considering there is in fact the product t naught. Now, a quick recap of what we have seen in this lecture. We asked ourselves the question, why not discuss the properties that led to the FRIs and SBRs, essentially the FIs, to possess the desirable properties of an inference system, that of monotonicity, interpolativity, robustness, continuity. Why not discuss those properties in generality, not only looking at it as being coming from the distributive lattice structure? And it meant that we need to discuss functional equations involving T-norm and the implication. And we have seen that not just the R implications obtained from left continuous T-norm, but there exist other families of fuzzy implications which also supply us with implications which satisfy some of these properties. So where you would like to use implications having those properties, it is not mandatory anymore to restrict ourselves to go only to the residual lattice structure or R implications obtained from left continuous T-norms. That's what we have seen in this lecture, at least with respect to a couple of functional equations that we have discussed. And our choice of choosing these two equations was also clear because they play a huge role in many of the properties that we have seen. Not only that, it can also be shown that these two properties lead to making our inferences computationally more efficient. We will see this during the course of these lectures in this week. In the next lecture, of course, we will try to answer the first question, that of generalizing some of the results that we have seen for FRIs where the operations came from restricted lattice structure to FRIs which employ implications coming from different families, family other than the R implication family. So in that context, in the next lecture, we will discuss the suitability of BKS inference mechanism where the implication is chosen to be an F or a G implication. This is what we will discuss in the next lecture. Glad you could join us for this lecture and hope to meet you soon in the next lecture. Thank you again.